next speaker is Professor Ting Yu, and he is also the chair of the physics department, and he has done a lot of very pioneering work in treating quantum open system problems, and his research actually covers a very broad spectrum, from entanglement to continuous quantum measurement to quantum phase transition. So let's welcome Professor Ting Yu. Tim, you can
Yes.
start now.
Can you see my screen?
Yes, I can.
Okay. So
Good.
first, I'd like to thank the organizer for giving me opportunity to report some results we have obtained in the last few years. So this is not really just kind of academic seminar. So I basically cover some results, not just for one project, so cover several things. And also being the last speaker, I think we have some kind of advantage because the previous speaker already made quite a nice preparation for my talk. So here, I mean, that's kind of well known because the first question is why quantum computers? So according to Moore's law, we know that, the idea is, the number of transistors on a macro chip would double every 2 years, which means eventually the system will become smaller and smaller. And the consequence is we have to get into the quantum regime. So that's the, somehow we cannot avoid. So that basically, the quantum computers basically become kind of a necessity, I mean, in the future. So that's why, it's become so important. So, I mean, here I'll just make, I think I like make a comment here by using the Feynman's code. So the idea for proposing quantum computer, actually, Feynman was among the first, the few pioneers in quantum computer research area. So in even 1980, so I think the first paper published in 1982, he proposed the, the ideas, if you use quantum computers, then it's likely you can simulate a quantum many-body system efficiently. Otherwise, we know that everybody doing in the quantum regime, we know that's extremely difficult to simulate a quantum system. So using a classical computer, we take not years. I mean, in many situations, I mean, it's kind of an impossible task to simulate a many-body system. So that's come to the situation, the why the quantum computer are so important, but why we haven't got one, so far. So the question is, there's many difficulties. I think Xiaofeng already pointed out, it's kind of a DiVincenzo criteria, which it just mentioned few. I think the decoherence is one of the most important obstacle to build up a quantum computer. So that's what will happen, what happened here. See, the noise is everywhere. So classically, we know how to handle noise, but in quantum mechanics, it's much more challenging and much more difficult. So that's the motivation for, the work we have been doing for the last 5 years. So try to understand quantum noise and how to control quantum noise and how to handle quantum noise. So that's the kind of motivation we have. So here, of course, mathematics could be complicated. So my focus wouldn't be just on the mathematics, rather on the conceptual aspect. So you have a quantum system, here, just for example, the atom. So you have a two-level atom here. So interacting with the environment can be complicated, can be a classical environment, can be quantum environment, it can be a kind of mixture. So also environment, you can think about like even vacuum. So vacuum is a kind of quantum environment. Then you can have many other type of environment. So overall, so that's why quantum noise is complicated and it's so difficult to build up a quantum computer. So I think that's basically, one of most important issue. I mean, when we try to accomplish, the mission to build up the first quantum computer. Although, you have seen the news, about this quantum simulator. I mean, about this D-Wave, and also many other companies, they try to build up first quantum computer, but so far, they are not really, in a sense, not a real full-fledged quantum computer. So it's kind of a quantum simulator consisting of many qubits. They are not really fully functional, but I think already, even in such kind of situation, they already become very interesting. So that's why, those proposals have attracted a lot of attention. I mean, over the last decade. So I think the work at Stevens, we have been focused on. So is more or less is on the understanding quantum noise and how to compute, control the quantum dynamics under the influence of noise. So that's the kind of a major issue here. So of course, I wouldn't really go into the detail here. So the major tool we have developed over the last few years is a kind of a stochastic Schrodinger equation. So everybody know in quantum mechanics, the most important equation is called the Schrodinger equation. So here we are interested in not just a pure quantum system, which means the pure system means there's no influence from noise. But here we are interested in this kind of called quantum open system. So open system, of course, as I said, earlier, so the open system are really universal. So in reality, no system can be isolated from environment completely. So that's why, classically, we have so many ways to deal with this. You have perfect error correction. You have, much more efficient control protocols. But in quantum mechanics, we already developed a kind of useful concept. But when we talk about the application, we still have a long way to go. So that's the I think that's the basic is the general motivation and also general method. So the key question is, so why we are interested in this non-Markovian noise? Because as I mentioned, there's many different kind of noise. You have white noise. I mean, the color noise is another name is called non-Markovian noise. So the color noise actually is a more general, much more general, So that's the case. So the white noise is just a special case. It's a mathematical simple case. Mathematically, I think it's really simple, but doesn't mean they cover everything. So I think I like this quote by von Kappen, non-Markovian is the rule. So which means if you don't really ignore, if you don't really ignore some details, if you really don't really assume, some kind of special cases, you always have non-Markovian. So Markov is kind of exception. So when you have a relatively weak interaction, you have a, broadband environment. So in that case, of course, you could use a Markov as a nice approximation, but that's not true. Okay, so I will just skip, all this kind of detail here. So I will concentrate, the several cases, how do we use non-Markovian trajectory developer, in our group in the last 5 years, to simulate, to compute geometrical phase, which is so important for geometric quantum computation, because, is widely known, if you use the quantum geometrical phase, you relatively have a robust quantum gate, realized in such a way. But, it's difficult to compute this geometric phase because you want to assign a quantum gate with accurate phase, then you need to have a better method, to know exactly how to realize such kind of phase. So that's the work, for the first project. The second one, that's for the different phase, for the different, this gamma here, describe the color noise, the different kind of level, so 0.1, 0.2, 0.2, that's depend on the 0.1 means this really very strong color noise. Otherwise, the color noise become gradually goes to the white noise. So that's the way to do this. I mean, you know to assign the geometrical phase, you have to have a better understanding of how the noise affect quantum system. So that's the the first problem. Second one is, so given this importance of the non-Markovian noise, or you can call it noise, how to measure them? So those are very important thing, because otherwise you don't know, given the system, given the noise type, right? You don't know how to describe, the system is a moment non-Markovian or less non-Markovian or so on and so forth. So that's what we have done last few years, try to find a way to characterize, different type of color noise. How do they affect the quantum system? What kind of typical feature we can capture, to have a better description of noise dynamics. So here, I just give you one example here, so the two-level item serve as a, qubit here, coupled with an optical cavity. Of course, optical cavity, by definition, you cannot be isolated from environment. So then automatically you have environment here. So the question is, how can you describe, the qubit time evolution? So then you see, typically, we can manufacture a high Q optical cavity, means the cavity only contain, for example, like one optical mode here. So means, the system, the optical cavity system actually is rather, somehow in a highly quantum regime, but still, the optical cavity will subject to the influence of environmental noise. So then how to characterize, the non-Markovian dynamics of item here. By item means, I mean just qubit. So then we use a kind of a new structure, using this quantum trajectory, then we get, the important non-Markovian master equation, we can just find some lot of new features, which can describe, because for this case, we have several couplings, the qubit coupled to the optical cavity, then cavity coupled to environment. So depend on the, we have two kind of couplings here. So then you have to think about the relationship between the coupling between the qubit and the cavity, and the coupling between the cavity with the environment. So there's a lot of kind of interrelationship between them. This is very, the interesting results. Here, described by the a new quantity is called non-Markovianity. It's a measure of the color noise. So of course, I mean, I just give you the picture here. That's the picture. So without giving you the equation, so we plot the a measure here. So over this coupling, so you can see, the with the kappa, because kappa means the coupling between qubit and cavity. So when this coupling here, this qubit and the cavity strongly coupled, so then relatively, the qubit will be behave like a non-Markovian system. So because, the cavity will cause, the decay of photon from atom. So if the atom, the interaction between atom and optical and the cavity is strong, so which means the photon won't really have a chance to escape to the environment. So in that case, of course, we expect a strong non-Markovian dynamics. So that's the this figure described. The stronger K, we have a better non-Markovian dynamics. So also here you see something like this is a highly non-trivial, because it's not simply just the dependence. So lambda is an important parameter describing the environment. So this also, the dynamics of a qubit, which of course is they are fundamental elements for quantum computers. So their dynamic is highly sensitive to the environment. So depend on environment is a white environment or colored environment. So in that case, you can see we see some important feature. It's not really doesn't mean if environment you can engineer environment. So if you have relatively, for example, you have a strong non-Markovian environment, then you could have the stronger non-Markovian dynamics for qubits. So that's, of course, from this one, that's not the case. So you see somehow there's a plateau here, there's some region, for the lambda, which lambda, as I said, is a parameter describing the non-Markovian feature of an environment. So here you see from about 0.5, here is a little bit more than 2 here in this region. So the non-Markovian for the qubit could be just doesn't really exist. I mean, so here you see, but when they, exceed, when the parameter lambda exceeds this threshold, then you see the, kind of the revival of non-Markovity from here. That's a really interesting feature. Just somehow you see not really somehow either monotonically increase or decrease. You see some kind of a very interesting feature about the dynamics of the of qubit here. Okay, so I think I have to go quickly. So another example is given the quantum memory. So quantum memory is you not just have one qubit here. You have n qubits here. So n could be, in reality, could be a large number. But for our numerical simulations, we cannot really handle 200, like 300 qubits. So that would be just mathematically is very complicated. So instead, we simulate up to 3, 4, 5, this kind of proof of principles. But in principle, we can just simulate as many as we wish, if we allow, the longer computation time. So here, that's the example. We have n two-level items here inside the optical cavity, assuming, the cavity also coupled to an environment, with describing by this function. This is called the correlation function. So correlation function just tell us the behavior of your environment, could be a Markup environment or non-Markovian environment. So that's the meaning of this correlation function. Okay, so I'm just take 2 qubits as an example here. I'm just showing you, by using the method we developed over the last few years, we can have somehow called a fast tracking of entanglement evolution, because entanglement typically is not a physical measurable thing, which means you cannot measure entanglement directly. So you have to do something, like to measure some kind of quantities. You have to do the numerical simulation, because the measurement, entanglement itself is not really directly measurable. So that's the way, we develop a new method which can be used to track entanglement evolution in a much more efficient way. So here is a trajectory. We use, for example, typically the entanglement is precisely described by the density operator. So this solid line is just by the density operator, but computing density operator need a lot of time. So as far as we know, using tomography to reproduce, the entanglement for the 2 qubits can take hours, a few hours to generate this one. So that means, if you want to do quantum control, in particular, the quantum feedback control. So you need to measure environment. You need to get the data, but the data, that's you have time delay. So you need to process information, which take too long time. So that's virtually make a quantum control impossible for this case. So now we develop a kind of technique, we can just use a single trajectory, which basically, you got just like a second immediately. So a single trajectory is very fast to generate. So then you can estimate, although you can see this dashed line is not really exactly the same as this solid black line. But dashed line capture the meaning, the feature of this entanglement. You can see entanglement have a, like a turning point here, also turning point here. So they basically follow the pattern, but just using single trajectory. So I think in terms of efficiency, this is really much more useful than using the density operator. So that's the kind of advantage of using quantity trajectory instead of density operator. So so the last one I think I like to just mention, that's called a quantum state transfer. So in particular, I'm talking about the Schrodinger cat. So Schrodinger cat, traditionally coined by Schrodinger. So think about the cat is in the superposition state. I think both the Igor and Xiaofeng mentioned this, what's called the superposition in quantum mechanics. So in reality, we never seen, the cat is in the superposition in the sleep and awake. Of course, originally they talk about, dead and alive, because now I love cat so much, so I don't want to see cat really dead or somehow. So, but anyway, so that's the case. So when we have a Schrodinger cat and we put a cat into the cavity, so when we can see that how does cat transfer from one cavity to other cavity, because of course, cavity are coupled. So basically this graph describes three cavity. So that's the, the three cavity, this is the, so the, the column. So you see the column, we have three cavities. So you can see the transfer, eventually starting from here, so the first cavity here, you can see the, the dark or the different color, this means, the initially because the Schrodinger cat is a superposition of coherent state, two coherent states here, alpha and minus alpha. So you see the interference. So here you can see the interference, right? So then gradually, because of this noise interaction, so, and also the dynamics, right? So interference pattern gradually disappear. Here, you can see this basically is typically, that's a kind of, you don't really see negativity here, means negative value. So which means omega t equal 1.4, the cap in the first cavity. This one just like coherent state, the cat means either in alive or in a sleep. So that's just a single coherent state. So we'll stay here. Then you see the second one. So second one, you never see somehow, the first one is a superposition here, right? Superposition typically for this case doesn't exist for the second cavity. So then you can see the hop between the first cavity and the third cavity, because initially you can see the cat was put in the first cavity, then gradually evolved to here, so then become a single coherent state. Second cavity, of course, initially there's no cat there. Then final state, no cat there. So the third cavity, you can see initially, of course, there's no cat here, right? So just a vacuum. Then eventually you can see, the cat transfer into the third cavity, almost entirely, but with the angle here, with the face, face rotation here. But
Okay, Tim,
so this one just capture everything. So I think that's basically that's all I want to talk.
Okay, great. Great. Thank you so much. And I guess for those who are able to stay longer, please ask questions if you have any for the speakers. And thank you everybody for joining our virtual research forum. And I'm sorry for the delay. So I guess I have no way to cut any of those very interesting talks. Thank you.
So no questions. Oh, can I typed the question. You ping. So what is the reason for the face?
So Professor Solana has a question for Tim.
Oh, okay. Okay.
But I'm just curious, what is the reason for the phase which emerges in this last example for the three coupled cavities? So yeah.
So that's just the evolution itself. I mean, you see, because we just choose this particular time, right? So this particular, that doesn't mean like exactly the the figure one. That's the superposition of you can see here. I will show you. So, okay. So that's the superposition here. Alpha plus minus alpha here. So I mean the phase is here. Instead of alpha, so you got alpha times I omega, some rotation here. So then typically, you have to find, I mean, for some particular time, you might see exactly just alpha, but in most cases, you would have like alpha times, adding a phase.
Okay, so it can be that at some point it will have zero phase, right?
That's right. So you have, for example, you have this particular case, yeah, that's right.
Okay.
So we just use this particular time, cutting this time, but you can see the pattern just exactly same. Of course, I mean, you have some environment there, right? You will have some noise, but I assume, for a perfect transfer, you have to assume the noise is relatively weak. Otherwise, you're going to see kind of decay of amplitude, not just a change of phase.
Right. And the coupling to environment is much weaker than coupling to the cavity.
Exactly. Right? Exactly. So the interesting is because the cavity 1 and cavity 3 in a symmetric position. So you can see the state transfer on the, the second one, because second one coupled to because this model is you have a chain there, right? Consisting of 3 cavities. If you have a loop, then you are going to see, I think, a transfer possibly to every set. But here, the number 1, number 3, they are in the symmetric position. And the number 2 is somehow coupled 2 cavities. So basically, number 2 serves as kind of platform. The cat, of course, cat has to pass the second one. But typically, it doesn't really stay there long. So, I think that's a very interesting situation here. I think more or less classically, we have this Newton's riddle. I think that's something like something similar. You have a just group of balls there. But the first one change, then you see the last one change, right? But nothing happened in between.
Maybe it's considered like a transitional state, right?
Yeah, that's right. So if you have, for example, the 4 states, you would see something similar, inside, so some symmetric state will behave differently.
So you may consider not 3 cavities, but 4 cavities, right?
That's right. 4 or 5, I mean, because this model itself actually, so that's what at a point I talked to Yuping, Yuping, his lab can do this kind of cavity coupling. I mean, can do this, but Yuping only have a cavity here, right? I think that would be great because we don't have an item, in this case. So it's only for
we need someone to bring their cat into our lab too.
May I also ask, or is the time out? I can also email.
Yeah, I think I will have to leave now. But Igor, I say that you are also the host, so I think we can keep this going. And thank you so much, everybody, and hope to see you guys very soon. Bye.
Thank you, Yuping. Yeah. And then Ting, I quickly ask you, since we're hosts, we can use our privilege. So I'm very curious. I was going to ask exactly what you mentioned, but I was going to ask it. So does it actually at any point, do you have at any point the state in the second cavity, which is also a cat state? So can one see analytically at any point in time?
Actually, we made a kind of video, right? Even exists there, but is typically we haven't seen any in our simulation. We haven't seen any kind of you see the figure can become a slightly complicated here, the tree distribution. Maybe not as nice as this one, but we haven't seen any kind of shape of a cat.
Right. Because that's what I guess. It could be that it never as a state. So it's not like that the state goes through, but it's some kind of interaction and phases.
Never really happen for the second.
So it could be that it never actually appears, this particular state in between.
That's what I suspect. Although, we have to do this, show this like mathematically.
Right, right. Which is really interesting. Yeah. Okay. Anyway, both thanks Ting and Hofeng. I mean, this was really interesting. So unfortunately, I have to run, but maybe I'll email you both also with a few more questions.
You have if anyone has any question, just can send me email. I mean, that's also we set up a separate time to discuss anything.
Thank you, Igor.
Okay. Yeah. Thank you.
See you.
See you.
All right. Bye, everyone.
Bye.